Hello and welcome to chemistry. So what we're going to talk about today is measurement. Remember, science is about expanding knowledge, trying to discover new things in the unknown. It's a little bit like walking into a room with all the lights off and trying to figure out what's in there. And so as a scientist, you're going to step into a dark room and you're going to discover a table or a chair. You're going to find out what's in there, and you want to capture that information, capture your observations, and share them out with others. Measurement is how you do that. So when you're taking measurements, what you're trying to do is not just figure out, that there is a table in the room, that there is a chair, but how wide is the table? How far from the door is the chair? Where is the edge of that table? Trying to get precise, trying to get specific about where the edge of that table is important. If you bring some groceries into that room, you want to be sure you know where to set the groceries, at least know where the table definitely is and where the table definitely isn't. The actual edge to the table, that gets a little bit harder to be precise about, but you can be clear on what you know and what you don't know. And measurements are how you do that. Measurements are how you demonstrate what you know and the limits to what you know. Now, when we're talking about measurements, one of the things to realize, we'll talk about a couple of things. First of all, we'll talk about the dimension. We'll talk about in what dimension the measurement exists and how to capture that information. We'll talk about representing measurements, both factor and label, value and unit. We'll talk about the practices of capturing measurements and how to record our certainty and where we're uncertain in the measurements that we capture. We'll talk about conversion and carrying uncertainty through conversions. We'll talk about scaling units. We'll talk about unit systems and bridging different unit systems. We'll even talk about using the extent of a substance in one dimension to figure out its extent in an entirely different and unrelated dimension. We'll talk about dimensional analysis. So conversion, significant figures, unit systems, factor and label, different methods of representing units, that's all on the menu today. Let's start with that dimension thing. So when we're talking about dimension is the facet of something or the factor of something. It's how far something extends in terms of a particular consideration. I mean, you've got some friends, right? If I talk to you about one of your friends and I said, could you get specific about your friend? Tell me about your friend. You might say he's smart, he's fast. My friend, she's really good with numbers. My friend is very tall. And I say, get specific, put some numbers to it. You say, okay, fine, 5. Okay, the 5 doesn't do me any good. I don't know if you're telling me your friend is 5 years old or 5 feet tall. We have to talk about in which dimension that 5 applies. And it's the same thing with when we're talking about substances, we're talking about things in chemistry. I mean, in geometry, it's pretty easy. When you're talking about geometry, I'm talking about this cube, for example. When we talk about dimension, we usually just mean height, width, and length, 3 dimensions, right? 3-dimensional objects. But when we're talking about substances in a chemistry lab, there's a lot more dimensions. When you're talking about, say, a diamond, or you're talking about water, it's not just height, width, and length. It's hardness, it's viscosity, it's color, it's clarity, it's density, it's boiling point. All of these are dimensions, facets of that substance. And when we take measurements, it'll be interesting to know when we get quantitative about matter, it's going to be important to know how far into each of these dimensions that substance extends. And that's a measurement. Measurement will tell us, for example, the hardness of the diamond, the viscosity of the water, and so forth. How many inches are in its height, pounds are in its mass, degrees are in its temperature. How far does this substance extend into each one of those dimensions? Now, when we try to say, well, how far does it extend? And we want to share that information with somebody else or with ourselves 5 years, 10 years from now, we need a unit system. When we say 5, we say not just how far does it extend in length, But what does 5 mean? We mean it extends a length based on, well, 5 units. How many of these units are in the length of that object? So when we're going to describe or we're going to capture our measurement, we have to give both things, the numeric quality and the number of units that we are counting with that numeric quality. 53 gallons, 1,200 feet, 21.5 degrees centigrade, 65.7 miles per hour. A measurement has to have both pieces, otherwise it's not a measurement. This is how we get quantitative about our observations. Okay, a little bit of history. So where do we get started with measurement? We've had measurements for a long time. As people were building bridges, as they were building statues, as they were building villages, the carpenter wanted to decide how long this piece of wood is and how tall is he going to be able to make the hut. So he would take measurements of the wood and he would take measurements of the place he wanted to build it and compare the two. Simplest thing to use when you're taking these measurements. Is your own body. So, for example, a carpenter might use his own feet to measure out the width of a wall, or he might use a cubit, his arm between the tip of his finger and his elbow, to measure the height of a stick of wood. And that's fine when the carpenter's working just by himself. But when he wants to share that information with something else, you need a shared or a common unit in order to accomplish that. As we started getting together and working cooperatively, we said, okay, let's not everybody use their own feet. Let's pick one person, use his foot or her foot as the unit of measurement. And that's kind of where we started. We said, okay, well, we've got a king. Let's use his feet. So we used the king's feet as a standard unit of measurement. And that was fine as long as we had the king and everybody agreed on it. But then maybe the king passed away, somebody else became king, and that person's got shorter feet and caused problems. So we looked for something external to be used as our units of measurement. The village stone is a common one. We would pick a stone and plant it in the center of the village. And we would say that stone, its width was our unit of measurement. Or that stone, its weight was our unit of measurement for weight. And that's fine as long as you can all get to the village stone. But as humankind started getting bigger and bigger and spanning more places, we needed a portable standard. One of the most successful units of measurement is the imperial units of measurement. The imperial units of measurement were started by Great Britain, and as Great Britain expanded and built an empire, they used the imperial units of measurement. And to have a portable unit of measurement, they standardized on a grain of wheat. Because when you set off on a new voyage, you always brought some wheat with you so you could plant crops and establish a colony and so forth. The first unit of measurement is 3 grains of wheat, end to end to end. That's called an inch. An inch was originally defined as 3 units of wheat. As you wanted to get something bigger, well, you just scaled off of that. So if we all agree on what an inch is, we can all agree what a foot is. It's just 12 of those inches. And then we can go up to a yard, a chain, a furlong, a mile. We can keep going up from that. We can also figure out how to use that grain of wheat to find volume and mass. And the entire imperial set of units was originally based on that grain of wheat. Yeah, I won't get into a lot more detail on that one, but we will come back to standardized units, and we'll find that there are things that are better than a grain of wheat to standardize on. But the next thing we should talk about is taking measurements. How do you get the measurements? Okay, so there's different kinds of measurements. The first kind of measurement is an exact measurement. On the screen in front of you, if I ask you how many blue dots there are, how many what do you see? I mean, you see like 1, 2, 3, 4. There's 5 blue dots. Everyone here will answer 5 blue dots. Why? Because we can all see the dots, right? We can count them. 1, 2, 3, 4, 5. If I ask you in your refrigerator how many eggs are on the shelf, You take a look. Maybe there's 4 eggs. 1, 2, 3, 4, 5. You can see each egg. So you know how many eggs there are. Exactly. No doubt about it. Everyone who opens that refrigerator door will see 5 eggs, see each egg, and say 4 eggs. If I ask you how many friends are around the table, you might look around and say 1, 2, 3, 4, because you can see each unit. This is an exact measurement. Exact measurements are very useful. Well, if you know the measurement exactly, there's no uncertainty. It's not like I have maybe a little bit more than 5 people at the table or a little bit more than 4 eggs. No, it's 4 exactly, because you can see the units. Exact units of measurement result just by looking at and counting the units. Okay, that's one kind of exact measurement. There's another kind of exact measurement too. If I asked you how many inches were in a foot, what would you tell me? You'd say 12 inches in a foot, right? If I came back to you and said, well, I got a foot over here and it looks like it's got 13 inches in it. Is that possible? You'd say, no, it's not possible. I said, why not? It's because that's what a foot means. That's the definition of a foot. If you have something with 13 inches in it, okay, you've got something with 13 inches in it, but it's not a foot. The definition of a foot is 12 inches. Every foot that has ever existed anywhere in the universe has 12 inches in it, because we all agree that if it doesn't have 12 inches, it's not a foot. So another way of coming up with an exact measurement is by leveraging off of definitions. By definition or by seeing the units, you can come up with an exact measurement. A foot measures 12 inches. Said another way, a 12-inch foot is an exact measurement. All right. Now, not all measurements are exact. We can also come up with measurements when we can't see the units, when we can't rely on a definition. We can use instrumentation to take measurements. Like, for example, you probably have a pencil on your desk. That pencil has a lot of qualities: hardness, mass, volume, and it also has a measurement of length. If I take a look at that pencil and I ask you, well, how many units are in that length? Maybe how many inches are in that length? Well, you can't see the inches. It's not like eggs on a shelf. You can't actually see each one of the inches. But you know it has a certain number of units in that length. If you hold a ruler next to it, you can estimate how many inches are in there by comparing it to the marks on the ruler. 1, 2, 3, looks like 8 inches in the length of that. 8 inches exist in that pencil in the dimension of length. And 9 don't. I can see that it doesn't get to 9. So it's 8. And in fact, it's a little bit more than 8, but it's not 9. Okay, so one measurement I can offer is 8 inches in the length of that. All right, let's talk about qualities of measurement. Then we'll come back to this to the challenge in front of us. If I hold up a penny to you and I say, okay, here's a penny. What is the width of that penny? Well, you can do the same thing. You can try to come up with how many, say, millimeters are in the width of that penny. One person might say 30 millimeters. Another person says 31. Another says 31.2. Do you see how those measurements are different? I mean, they're all trying to talk about the millimeters in there, but each measurement adds a little bit more detail to it. It gets more precise. Precision is a quality of measurements. Yeah, there's 30 millimeters in there. And you know what? Maybe there's 31 too. Maybe 31.2. I'll buy that. I believe that. But 31.2534556? What confidence do you have in that degree of precision? So the measurements, these 4 different measurements here, they are all measurements of, say, the width of a penny, and how they differ is in precision. Now, if I pull up a ruler and I compare the penny to the ruler, one of the things you might find is that, well, the ruler says there's actually only about 20 millimeters in there. So in addition to precision, there's an issue of accuracy. Accuracy is how closely the measurement matches to reality, how reproducible it is, how verifiable it is. So measurements can differ in terms of precision. They can also differ in terms of accuracy. So for example, if I told you that penny has 20 millimeters in it, instead of telling you it had 30, well, the precision is the same, 20 or 30, the number of figures in the measurement, but the 20 is a more accurate measurement because it's more reproducible. If I take the measurement, somebody else takes the measurement, someone else does. If you compare it to a ruler, it looks like about 20. People aren't going to find 30 very often. So the 20 is more accurate. If I told you that it had 25 millimeters in it, I mean, that's a measurement, and it is a more precise measurement, but you might take a look at that ruler and question that, right? I mean, look, it hits right about 20. It clearly doesn't stretch to 25. Therefore, that measurement is precise, more precise, but it's not accurate. So when we're taking measurements in the lab, we want to strive for both precision and also for accuracy. If I told you that penny has 19 millimeters in it, well, that's kind of hard to see on the ruler, but we can't really dismiss it. And it is more precise than 20. But if we compare it to, say, the other side of that ruler, then we can say, I can buy that 19. In fact, if I told you that it had 19.5 millimeters in there, I can see that it's at least 19, and I can actually see that it's not 20 yet. So 19.5, that is a reasonably accurate measurement. In other words, if I took the measurement, you took the measurement, we could both see that it's more than 19 and it's less than 20, and we're both likely to put something like, 19.5. It's reproducible. On the other hand, if somebody put on that 19.355, what do you think the odds of that being reproducible? Two people getting the same measurement? Okay, that's not accurate. It's not something we can trust. It's just calculator noise on the end of that. Accuracy and precision are both considerations when we talk about taking these measurements. And you are always obliged, when you're in the lab, to take the most precise measurement that is still accurate, that is still reproducible. All right, there are different kinds of instruments you're going to be working with. There are graduated instruments, and there are digital instruments. I'll show you how to read each of those. Graduated or analog or scale instruments have a scale on them. And what you're doing is you're comparing that scale to your object, and you're trying to record a number. Digital will actually kick out a number. Now, when you're working on an analog measurement, if you see something like this, I don't know if that's if that's a scale and it's telling me a weight in grams, or if that's a ruler and it's telling me a length in inches, or a graduated cylinder and it's telling me a volume. But I can see that that red triangle is somewhere between, it looks like 8.9 and 9. It doesn't quite reach to the halfway mark. When I'm trying to read that instrument, what I'm going to do is put down is everything that I'm confident in, that I'm certain in, and I'm going to put nothing that is a claim that I can't back up. And there's always a gray area between the two, between the stuff that I'm certain of and the stuff that I'm uncertain of. And there's a place for estimation. And you are obliged to put everything you are certain of and a reasonable estimate to the next digit, and nothing beyond that. So in this case here, I would say that if somebody wrote 8.94329 grams, well, the 8, there's at least 8 in there, and there's at least 8.9. We can see that because the red triangle is past the 8 mark. It's past the 8.9 mark. The 4, well, it's not halfway between the 8.9 and the 9 and the 9.0. So the 4, that's a reasonable estimate. Stuff beyond that's just calculator noise. The 8 I can trust, the 9 I can trust, and the 4, that's a reasonable estimate. The 3.29, That's fiction. So what am I going to record in my book? I'm going to report 8.9.4 grams. Now, if you saw this as a little bit differently than me, and it looks like it's not 0.4 but it's 0.3, and you recorded 8.93, neither of us is more right than the other person. There is always some uncertainty in that measurement, and nevertheless, you are obliged to make that estimate between the smallest two marks on your graduated instrument. You're always obliged to make a reasonable estimate. And 8.94, 8.93, these are both reasonable estimates. Someone who put 8.99, we can both see that that triangle isn't more than halfway between the two. That would be an unreasonable estimate. But every measurement that you capture, you are obliged to put everything you're certain of and an estimated digit. You're obliged to put in a reasonable estimate based on how far between the two smallest marks your reading is. Let's try it. Let's experiment here. Okay, this paper clip here. If I asked you how many centimeters exist in the length of this paper clip, what would you put? Well, you'd start by saying, well, this ruler, this instrument that I'm using, its smallest marks are in centimeters. So I can look at this and I can say, well, it's got 1 centimeter, it's got 2 centimeters in there. It doesn't have 3. So I could say 2 centimeters. And if I recorded that, what do you think? Do I think I'd get full points? Remember, you're being paid to collect measurements. If you leave any measurements behind, that's like leaving money on the counter. If you're working for a company and they're asking you as the scientist to take measurements, if you just put the stuff you're absolutely certain of and nothing else, you're leaving some truth behind. Now you can tell that that's more than 2, right? It's not 3, but it's more than 2. And you can make a reasonable estimate between the two smallest marks, between that 2 and that 3. What would you estimate? I mean, if you put 2.0, is that a reasonable estimate? Or are you leaving some truth behind there, right? I mean, that's clearly more than 0.0. It's clearly not 0.9. All right, you could put on there 2.4, for example, and that would be a reasonable estimate. And that would have value. That 0.4, the 4 isn't absolute, isn't 100%. I wouldn't bet my life on the 0.4. But I wouldn't leave it behind either. It's part of our measurement. And if somebody else put 2.3 on there, for example, if you're in the laboratory or if you did this on a test, you'd get full points for 2.4 or 2.3 because you can't tell the difference. How about the person who puts D, 2.9? Do you think they're going to get full points? No, because the 0.9 is clearly not a reasonable estimate. The 2.0 is not a reasonable estimate. And if you just put 2 centimeters, man, you left some money on the counter. And it ain't your money to leave behind if you're working for someone and capturing measurements. So if you put A or D, you'd get this wrong. But F or G, either one of those, you'd get full points. All right, here's another one. Now I got a better tool. I got a better instrument. I've got something that has centimeters on it, and I've got something that has tenths of a centimeter on it. Can you see that line on there? So if I put 2.3 on this one, would I get full points? No, because I can tell that it's got 2.3 in it. The question is, how much more than 2.3 does it have on it? And again, look at the two smallest marks. Looks like it's got at least 2.3, but not 2.4, so it's somewhere in between. So you are obliged to estimate how much in between. If it's really tight like that, well, just call it a half. So you could put 2.35 and you would get full credit. If you put 2.4, you would lose points. If you put 2.40, you'd also lose points because it's clearly not all the way to that. But if you scored 2.35, or if you even wrote 2.36 or 2.33, you would get points for it because you put what you were certain of, the 2, the 0.3, and you put a reasonable estimate between the two smallest marks. All right, this is how you work with graduated instruments. Now there's some instruments behind me. Let's call this, this could be a scale, but let's call this a thermometer. And the one on the left, what's the measurement you're going to record in degrees Celsius? I mean, that pink line goes at least to the 20. It goes at least to the 21. So what am I going to put? 21 degrees Celsius? No, it's going past the 21. So I'm going to say, I don't know, 21.2, 21.3. That would be a reasonable estimate. How about the one in the middle? The one in the middle, what would you put as your measurement for that? It's got at least 20. It's got at least 21. It's got at least 22. And now what's the amount between 22 and 23 that you would reasonably estimate for that estimated digit? It's 0, right? I mean, it looks like it's right on the mark to me. So I would probably put 22.0. I have to put something for that next digit, even if in my estimation it's 0. You always have to estimate between the two smallest marks, even if what is between the two smallest marks counts as 0. Making sense? All right, the next one, I got more graduations. I have smaller marks, like 1/10 of a mark. Now on that one, I can see that it's at least 22. It's more than 22. It's more than 22.1, but it's not 22.2. What would you put? On a test, what would you put? In the laboratory, what would you put in your notebook? I'd put something like 22.12. If you put 22.13 or 14 even, I couldn't argue with you. It's the 2, the 20, the 2, the 0.1, we're all certain of that. And that 0.02 part of it, that's significant too. There's some truth in that, even if it's not bulletproof, even if it's not 100%. All right, so this is working with graduated instruments. Now be careful when you're working with liquids. Liquids have another trick. We'll talk about this in the near future. But the top of the liquid curves. So when you're working with a burette, when you're working with a graduated cylinder, you got to say, well, where's the top of the liquid? Is it on the edges or is it in that centerpiece? All right, I'll tell you right now, when we make glassware, the people who blow the glassware, who do the hard work of building this glassware, we pay them very poorly. The guy who makes the big bucks is the guy who writes the little lines on there. That's the guy who makes the big change. And he does that. The reason we pay the guy who just draws lines, as opposed to the guy who builds the whole burette, builds the whole pipette, the graduated cylinder, is because he calibrates that instrument by comparing it to liquids, by putting the liquids in and then pouring them out and seeing what it is. He will calibrate the measurements based on the center of that meniscus, the lowest point in, say, an aqueous meniscus. So when you're reading this, you are looking at the bottom of that meniscus for solutions that are based on water or similar to water. And it's very important that when you do this, you bring that instrument up to eye level. Don't look down at it. Don't look up at it. Keep it at eye level. That's because when you're trying to find the bottom of it, the bottom will seem higher if you're looking up at it. And it will seem lower if you're looking down at it. So in order to make the reading reproducible, always keep the level of the liquid right at eye level when you take that measurement. And look at the bottom of the meniscus for aqueous solutions. I'll warn you, there are some substances where the meniscus of the top isn't concave. In other words, the edges are higher than the center. Sometimes it's convex, where the center is higher than the edges. In either case, read the center of the meniscus, the bottom of the cavity, or the top of the convex form on the top of that solution. So if you're reading, say, a mercury thermometer will have a rounded top, not a cavity. When you're reading the mercury thermometer, still read the center of the meniscus. It's going to be higher than the rest of the mercury. And if we agree on that standard, then our measurements will be reproducible. And like I said, They're already calibrated by someone who went through and did it using that standard. Okay, so that's when you're taking measurements from graduated instruments, from analog instruments. How about digital? Okay, digital. Everything's digital these days. When you're looking at a digital instrument, like a scale, if I put something on that scale, I'm going to see some fluctuation. I put the beaker on the scale and it says 1.5782, 1.5783, 1.8, and you're going to see some fluctuation in there. But you're also going to see some consistency. So if these are each of my measurements, well, the 1 is very consistent, the 5 doesn't change, the 7 seems rock steady, and the next one is where I'm seeing some fluctuation. And after that, it swings wildly. So what I'm going to record is the stuff that is reproducible, stuff that is accurate. So I'm going to record the 1 and the 5 and the 7, and I'm going to record the digit that changes a little bit. If it goes 3-4, 3-5, 3-3, that middle digit, that's where I take my estimate. So in this case, I might say 1.573. Oh, the 3 is pretty accurate. The 2, I guess, is where the fluctuation is. 2-1, 5731, 5732, 57. That's where the fluctuation is. But it still stays around 2. So just like with a graduated instrument, I have the parts that I'm certain of, and I have the parts that are estimated. And the rest of it, that's calculator noise. The other digits have no significance. If you put them down on your paper, you're claiming there's some truth in them. And when you hand that in, when you save your notes, when you turn in your report to your client or your boss, you're giving them false information, and you're going to have some problems with that. All right, so that's how you read an instrument that is digital. Whether you're talking about a digital scale or you're talking about a digital thermometer, that's a quick and dirty way of capturing your measurement in a reproducible fashion. All right, now let's talk about reading somebody else's measurements. I mean, when you capture your measurements, you're going to know what is significant and what is not, and you're only going to write in your book what is significant. And when you come back and look at it later, you know where the significant ends. But science is a collaborative enterprise. We don't do science by ourselves. Any knowledge that you gained and you never shared with anyone, it's going to blink out of existence when you do. You're not expanding human knowledge, which is our objective, which is our goal. So we have to share our measurements, and we have to come to ways to share our measurements. When you record these measurements in a book, always record both the factor and the label, the value and the units, and only record the significant digits. And that's okay, if you're there with your buddy and your buddy says, well, wait a minute, this digit here, is it significant or is it not? And why would that happen? I mean, you're only going to put the digits that are significant, right? Well, no. Sometimes you are going to put down digits that are not significant because you need them for another reason. Let me talk about zeros. If I take this measurement, now I'm not measuring the height of a book. Now maybe I'm measuring the height of a building. I use a laser or something. Or maybe I just run a tape measure down the side. Or I use some other digital instrument to measure the height. Do you see how, as I'm taking this information, there's some variations? I mean, the 2 and the 3 are rock solid. After the 2 and 3, that's where it gets a little bit uncertain. So I record my certain digits and my estimated digit. Now I got to put some zeros on the paper to differentiate between, say, 23 million and, 23 feet. There's a big difference between 23 million feet and 23 feet. So I put some zeros on there just as placeholders to show where the decimal point is. And I recorded my book, 23 million feet. Now somebody else does a measurement. This guy maybe has a better tool. And you see when this guy does his measurements, when this next scientist does their measurements, that's my measurement. Here's his. 23,000, 23,000, those zeros. Do you see the zeros after that? In his measurement, and my measurement, that's just a placeholder. but he's actually seen a reproducible digit that's greater than 9 and less than 1. So what does he puts in his book, the length of sample B is, well, he puts the same thing I did, 23 million. It's just that some of his zeros are actually significant. They're not just placeholders. And here's the thing. Mine only had 3 significant digits. His had like 7 or 8 significant digits. But the thing we recorded looks the same. He knows to trust those zeros. I know not to trust mine. But if a third person comes up and gives us their data, and we don't know how they got it, we don't know whether to trust those zeros or not. All right, so this is the problem with zeros. Zeros are used in 2 different ways, and that creates some confusion. They're used as a placeholder to show you where the decimal point is. And they are possibly a measured quantity between 1 and 9. So here's the trick. When you are recording this information, you know what zeros are significant. But when you are reading somebody else's measurements, well, you have to take the most conservative estimate. You have to treat any zero that you can't absolutely trust as insignificant, as just a placeholder. All right, so how do you know if a zero is significant or not? Well, the safest thing to do is to follow these 4 rules. All non-zero digits are significant. There's no reason to put a 9 on your paper or a 7 on your paper unless it's part of your measurement. So if somebody put, 97, I'm going to trust both those digits. A 0 is significant when it is between 2 non-zero digits. So someone put 907, I'm going to trust that one. A 0 is not significant when it is before the first non-zero digit. And a 0 is not significant when it is the end of a measurement that doesn't have a decimal point in it. Let me show you why. Let me walk you through this here, okay? So, like I said, if it's there's no reason to put that 7 in 6.17 degrees Celsius on there unless it was either something that I'm certain of or something that I have a reasonable estimate for. So that's got 3 significant digits. The 175 gallons, again, all 3 of them are significant. That 12,213, all non-zero digits are significant. There's 5 significant digits there. All right, now, if I have a 0, it gets confusing. But as long as the zeros are between non-zero digits, it's okay. 1.07, again, there was no reason to put the 7 there unless it was significant. And if I can tell with the precision of hundredths, then I can tell with the precision of tenths. So that 1.07, that's still 3 significant digits, because even though that's a 0, it's between 2 non-zero digits. I can trust it. 105 gallons, also trusted. 21,003 feet, still 5 significant digits. All right. Now's where it gets a little bit more confusing. Let's say somebody tells me 0.07 degrees Celsius. Or 0.052 miles per hour. How many of those digits are significant, are part of my measurement, and how many are just placeholders? Okay, when a number starts with zeros, the only reason to start a number with zeros is to show where the decimal point is. That 0.052, that's helping me understand that I'm talking about 0.05 of a miles per hour, not 52 miles per hour. So that 0 is only there as a placeholder. It's not significant. It's just a way of showing me the magnitude of my measurement, the scale of my measurement. And the same with 0.07. There's only 1 significant digit in that temperature measurement. Now, when I put it on the end, though, that's where it gets a little bit confusing. That's where we have to make a conservative estimate. Zeros at the front of the number, never trust them. Zeros in the middle of the number, always trust them. Zeros at the end, okay, this is where you have to apply the most conservative analysis. That 2,100 feet, maybe those zeros are significant, maybe they're not. And if I'm building a rocket or I'm building a drug, I'm doing something where someone's life or their fortune may depend on it, I'm not going to trust those zeros. So what do you think? If I asked you how many digits many significant digits are in 2100 feet? How many can you trust? What would you say? You'd trust the 2, you trust the 1. Those zeros, maybe they're significant, but you can't know. So you say they're not. They're not significant when you read someone else's measurement. 2100 feet has 2 significant digits in it. 100 gallons has only how many significant digits? 1. There's only 1 significant digit in there. When the zeros are on the end of a number, if it doesn't have a decimal point, you can't trust them. You discard them. You say they are not significant. I mean, you keep them in your number to show where the decimal point is, but you just treat them as placeholders. All right. Now, in contrast, if there is a decimal point in the number, then the only reason to put the 0 on the end of it is if it is a measurement. 1.00 degrees Celsius, I don't need those zeros on the end to tell me where the decimal point is because I've written the decimal point explicitly. So if that's the case, then if they're not there to show me where the decimal point is, the only other option is they are part of the measurement. 100 degrees Celsius has 1 significant digit, but 1.00 degrees Celsius, hey, you tell me, how many significant digits do you see? There's 3, right? Those zeros, I can know they're significant because they're not placeholders. How about 100 point gallons? 100 point gallons. How many? I mean, 100 gallons is 1 significant digit, but 100 point, that's got 3 significant digits. Those zeros you can and should trust because there's no reason to put that trailing decimal point there if they were just placeholders. When I put that trailing decimal point there, I'm telling you, I'm making it clear, hey, trust the zeros. That's a tool for describing the significant digits. Similarly, the 52.0, there's no reason to put that 0 on the end of it after the decimal point unless I'm taking a measurement. Just like there's no reason to put that point after 100 gallons unless I'm trying to tell you something. I'm telling you those digits are significant. So zeros on the end are significant if you have a decimal point. All right, so this is how we, this is measurements, this is how we take measurements, this is how we record measurements, and this is how we interpret other people's measurements. Let's talk about scientific notation. Scientific notation is a great trick because you've already seen that being clear about significant digits, it can have some challenges. But scientific notation, I mean, people will tell you, your book probably tells you right now, scientific notation, you use it to record really big numbers, like, how many atoms in a drop of water, or the really small ones, what is the width of an atom. Scientific notation, the way it works, is the way scientific notation works is you take a look at how many zeros you are working with here, and you factor them out. So if I've got like 100,000 is equal to 1 times 10, 5 times. So if I factor out those tens and raise it to a power of 5, I can describe that number more concisely as, say, like 1 times 10 to the 5th. Now, if I have a number like 27 million, I can factor out a 10, another 10, another 10, another 10. In fact, I can factor out a total of 7 tens here, and then I can describe my number as 2.7 times 10 to the 7th. And if I have 40 tens in there, okay, then that's really going to save me a lot of pen ink. So it is useful for describing really big numbers. It's also useful for describing really small numbers, like in this case, but now I'm not factoring out a 10, I'm factoring out a 10 to the minus 1, or a tenth. And if I factor out a tenth once, twice, 3, 4 times, then I can write that number more concisely as 9.2 times 10 to the minus 5 to describe a really small number. So scientific notation is good for describing big numbers and small numbers. The scientific notation has 3 parts. It has the sign, it has the significand, the thing in front of the exponential term, and then it has the exponential term. Those 3 pieces together represent a single number. Note, this is not a a mathematical equation. I'm not saying 4.7 and then times 10 to the minus 2. This is a way of representing a single number, which is represented as 4.7 times 10 to the minus 2. That is a representation of a single number. It's important to differentiate between an equation and a single number, because as we find, we're going to, as we manipulate these things, understanding that it is a single measurement is important. But when you put a label on the end of it, like milliliters, you make it clear that this is a single number, just represented using a different kind of notation, scientific notation. All right, so we can use scientific notation to describe really big and really small numbers. And you should be comfortable going back between, well, standard notation, the way you're used to writing numbers, and this one where we factor out the tens or the tenths. So for example, if I had 0.053 milliliters and I asked you to represent this in scientific notation, well, that's okay. You just take the decimal point, slide over once, twice, and say 5.3 times 10 to the, what is it? Is it 10 to the second? No, I'm messing with you. It's a small number, right? So it's going to be a negative. I'm taking out tenths. 1, 2, but I took out 2 tenths, so it's 5.3 times 10 to the minus 2. And then you got to use your label, factor and label. 5.3 times 10 to the minus 2 milliliters. 320 grams, factor it out, but I'm taking out now tens instead of tenths. Still taking out 2 of them. That's what? 3.2 times 10 to the second. Okay. Now, if I want to describe each of these, each of these numbers, what's the first one in scientific notation? Write it down on a piece of paper. Slide the decimal point over, what, 2 times? It's a small number, so it's going to be a negative power. 1, 2. 1.7 times 10 to the minus 2. The one above that, I'm going to factor out 1, 2, 3, 4. 4 tens. What are you writing for that? 1.2213 times 10 to the 4th feet. All right, now here's the thing. Here's the real power of scientific notation. That significand, the part in front. I mean, when you use scientific notation, you always have a decimal point. So you don't have to show where the decimal point is. Moving the decimal point over takes care of that. So you only have to write the significant digits. That's why we call that part in front of the exponential term the significand. So how many significant digits in that one? The 2 and the 1 are significant, right? The zeros after that, well, we can't trust them, so we leave them out. So 2.1 times 10 to the 3rd. How about the one underneath it? Is that the same thing? Like 2.1 times 10 to the, that'd be second, right? No, because the zeros there are significant, and therefore they are included in the significand. 2.100 times 10 to the second. Miles per hour. See, this is the power of scientific notation. It gives us clarity on what the significant digits are. All those problems with zeros, they go away if you represent your number in scientific notation. All right, so we'll play more with scientific notation, but the scientific notation is a good way of being clear about your significant digits. All right, now with a word about calculator use. Okay, be careful. When you learn to drive or when you're learning to drive, I strongly suggest you don't go out and get a Ferrari. A Ferrari's got a lot of features that will only confuse you as you're learning to drive, and it will be a lot more tragic when you slam it into a brick wall. But the bottom line is the Ferrari's got so many more tools, it will only get you in trouble. Keep it simple. Get something simple when you're learning to drive. Okay, you're learning to drive now. You're learning to drive a calculator and instrumentation's in the lab. My suggestion is get a cheap calculator. It does need more than a grocery store calculator. You need the 4 functions plus addition, subtraction, multiplication, division. You also need logs and you need scientific notation. So you can't use a 4-function calculator. And you also can't use a smartphone on tests. You need a nice, simple calculator. But don't go out and buy, one of these high-end calculators that cost you like $200-300. They are like driving a Ferrari. They'll just get you into trouble. Get something nice and simple. Let's see. My suggestion is just hit eBay. I picked this one up off of eBay. It's an HP 20S. They haven't made this calculator in, I don't know, a couple decades probably. Well, at least a decade. But it's nice, it's reliable, and it's simple. It won't get you into trouble. Texas Instruments makes a new one that you can use, the 30X, the TI 30X. That's another good one. That's in most bookstores. Buy something simple. Either pick it up off of eBay or just get the simplest one you find in the bookstore that has scientific notation and has a log key. Look for that log or an LN key on there. And all these expensive graphing calculators, they're like a Ferrari. They're only going to get you in trouble. Also, it'll be tragic. You don't want to take calculators. Chemist calculator is like a boxer, okay? It's going to take a lot of abuse. And the simple fact is, if you think like spilling a glass of water on a calculator is bad, wait until it's a glass of hydrochloric acid. The stuff that's going to happen in the laboratory, that calculator, it ain't going to stay pretty long. So just get one that gets the job done, keeps it simple like a good boxer, and don't worry about these high-end stuff. You can play with those in a future class. Like I say, you can get these off of eBay. I think eBay is a great source for it. You can pick, if anyone asks you to pay more than $20-30 for a calculator, just go to the next one or come back in an hour. You'll find a cheaper one. All right, now using scientific notation on your calculator. This can be tricky, okay? Scientific notation, you know what it is now, but how do you use it? How do you put it into your calculator? All right, all the calculators that I'm familiar with, the way you put scientific notation in is with one of these four keys: E, EE, EXP, or times 10 to the X. Now, remember I said if you buy like a Ferrari calculator, it'll have a bunch of keys that'll just get you into trouble. Even the simple ones have like a 10 to the X or a Y to the X key. Never use this key for scientific notation. It will get you into trouble. It's like being in the wrong gear in a Ferrari. You will have problems. I mean, the worst part is it'll work sometimes, but 1 out of 5 times or 1 out of 4 times, it will give you a completely wrong answer. And you won't know that it's wrong enough to stop using that key. So look on your calculator right now. Look for a key that says E or EE or EXP or times 10 to the X. That's a good key for scientific notation. That's a way of telling your calculator, I'm not entering an expression. I'm not entering two different numbers related to each other. I'm entering this as a single measurement, a single number. 2.5 times 10 to the 5th is a single number. As opposed to telling your calculator, I want you to take 2.5 and multiply it by 10 to the 5th, an expression. The reason that's different, well, I'll show you. I'll give you an example in a minute. But that will mess up your calculations some of the time. So even if the 10 to the X or the Y to the X key seems like it's working for you, don't do it. Because on a test, when it really, the rubber meets the road and it really counts, that's when it'll mess you up. Here, let me show you an example. If you take the following number, looks like 25,000, and you want to put it into your calculator as 2.5 times 10 to the 4th, the way you put that into your calculator is 2.5 and then the E or the EXP key to the 4th. And then hit equals, and that will show you the number. If you use the wrong key for this, you're going to have some problems. Here's an example. If I told you 0.0416 or 4.16 times e to the minus third, the way you would enter this into your calculator is you type the significant digits, 4.16, and then e minus 3. Note, not e 10 to the minus 3, just 4.16 e to the minus 3. And if you hit return, you'll get you will get the correct answer. Now, if you type that in wrong, your calculator would show a number greater than 1. Yeah, here's a way of testing yourselves. Take 20.8 and divide it by 5 times 10 to the third. If you type that into your calculator, if you type 20.8 times 20.8 divided by 5 times 10 to the third in your calculator, and you use the right key, you're going to get a number, well, 20 divided by like 5,000, less than 1, 0.0416. If you hit the wrong key on your calculator, if you use that 10 to the x or the y to the x, your calculator would be thinking you're giving them the expression 20.8 divided by 5 times 10 to the third, and you would get a number like 4,000. So just try the calculation right now. If you get a number that is less than 1, you're using the right key. And if you get a number that is greater than 1 as an answer, you're using the wrong key, and you want to get out of the habit of using that key right now, because on a test, there will be a question like that. Again, look for the key that says E, or EE, or EXP, or times 10 to the x, not 10 to the x. Okay. All right. Another thing to be careful with on your calculator is the display mode. More advanced calculators have a way of displaying different set of digits. You want to have your calculator always in the mode of showing you all the digits. And we'll talk about how to round things off in a minute, but you want to make sure at least the calculator shows you all the digits that it has. If you're ever uncertain if your calculator is in the right mode, take 1 and divide it by 3. If you see a screen full of 3, 0.3333, your calculator is in the right mode. If you see something shorter, like 0.33, your calculator has been set to display only 2 digits. And if your calculation can give you a number with 5 significant digits, you've just thrown away 3 of them, and you'll get the wrong answer. So if you ever uncertain if your calculator's in the right mode, 1 divided by 3 and see if it fills the screen. If it doesn't, it's in the wrong mode. By the way, if your calculator, if you take 1 divided by 3 and hit return, and it shows 1/3, there are some calculators that will do fractions, or that have the mode of working in fractions. Turn that mode off. You bought a Ferrari and you're going to get into trouble. Turn that mode off. Look at the manual for the calculator. All right, so like I said, you want the calculator to give you all the gory details, show all the noise, but you have to rein in that noise. You have to know when to cancel the significant digits. Now, the calculator, your calculator is a great toy. I love my calculator. It's a wonderful tool, but it doesn't understand significant digits. So when you do a calculation, you're going to have to rein it in. You're going to have to find the significant digits. I'll show you how to know them in a minute. And then you have to cut them off and round the number where the significant digits end. All right, so how do you do that? The rule is if it's more than 50%, you round up to the next one. If it's less than 50%, you round down. So when you want to round the number off, you go to the place where you're going to round it off. You go to the next digit, and if the next digit is 4 or less, basically less than 50% of the next digit, just cut it off and you're done with it. And if it's 5 or above, 50% or more, you round the previous digit up to 1. Let me show you what I mean. So this one here, let's say I did a calculation. My calculator told me 0.017534, and I wanted to round it off to 3 significant digits. Where would I cut it off? Would I cut it off after the 7? Or maybe after the 1? No, wait a minute. Those leading zeros are not significant. So the 1, the 7, and the 5 are significant, and the rest is calculator noise. So I do my calculation, 0.0175. I want to round it off between the 5 and the 3. What do? Just draw a line after the 5. What's after the 5 is less than 50% of the way to the next digit. So I just throw it away. That 3, 4, it's less than 50%. I throw it away. Okay, the number in front of that. The first 3 digits are significant. So if I do my calculation and my calculation tells me I can only trust 3 significant digits, the 1, the 2, and the 2 I can trust. The 1 and 3, they look significant. If somebody told me a measurement with that, I would assume they're significant. But if I'm doing the calculation myself and I know that 1 and 3 are not significant, I need to get rid of them. So what do I do? Just write 122? No. 122 and 12,213, those are not the same number, rounded off. I mean, if I owed you $12,000 and said, hey, can I round it off? Can I pay you $122? You wouldn't buy that, right? All right, so I got to use zeros. So I take the 122, the digits after that are less than 50% of the way to the 1, 2, 3, so I throw them away, and I replace them with zeros. All right? I could write 12200, or I could put it in scientific notation, 1.22 times 10 to the 4th. Okay, now on the next one, that's very similar, but do you see how the 5, 7 is more than 50% of the way to the next digit? Okay, what would you write if I asked you to round that off to 3 sig figs? You'd write 12300, or in scientific notation, you would say 1.23 times 10 to the 4th. How about the last one? What would you put for that? First, I mean, there's a lot of digits there, and if I just wrote that, you'd say they're all significant. But if I'm doing the calculation, I know that the last half of it is calculator noise. I take the 9, I take the 2, and I take the 1, but 6, 8, that's more than 50% of the way up. I round it off to 92.2 or 9.22 times 10 to the 1st. All right. Okay. Now, how about, let's see, how about these numbers? That first number, if I asked you to round it off to 3 significant digits, well, the first 3 are significant, and then I got the 2, 3, 5. So just get rid of that, so I write 100, right? Be careful. That's a trick. If you write 100, that's only 1 significant digit. So if you want to represent 3 significant digits, you can't just write 100. You would have to show that those zeros are significant. One way to do that is write 100 point. That works. Now, if you've got 82.035, again, 820 are significant, the 35 are beyond significance, I'm going to throw them away. I would write 8.20 times 10 to the 4th. I can't just write 82,000 or even 82,000 point, because the first one, that's representing 2 sig figs, and the second one is representing 5 sig figs, because zeros on the end, they're significant if I put it. So if I want to show 3 significant figures, I can't do the first one, I can't do the second one. The only way I can represent the correct significant figures is with scientific notation. And you are going to find that some numbers, as you start working with these things, can only be represented accurately and correctly with scientific notation. So that's going to be an important tool in your toolkit. All right, but how do you find out? When I do these calculations, when I take 2 numbers, 2 measurements where I know the significant figures of each and I multiply them or I add them, how do I find the stuff? How do I round off the calculator noise in my calculator? How do I know where to round it off? All right. First thing to realize is, and I'm going to lie to you here, we'll say that there's a different process or different way for addition and subtraction as opposed to multiplication and division. It's not really true. It really is the same process. It's just hard to see that it's the same. So it's easier to understand it if you treat it like 2 different processes. Of the 2, you're going to like multiplication and division easier. It is better because it is easier. The addition and subtraction is actually the hard one. But if you've got 2 numbers and you want to find the significant digits in your calculation for multiplication and division, well, that's pretty simple. All you got to do is look at what's going into it. That first number has two significant. So does the third one, 42, two significant figures. 6.3, two significant figures. So when I do my calculation, when I crunch through with that calculation, my calculator, because I've set it to show me all the digits, it's going to say something like 4,498.2. But some of that's calculator noise. All right, I can only keep two significant figures. The rest is noise. So I have to round that off to two significant figures. So I keep the 4, and I round off the rest, which means I'm going to have to make that second 4 a 5. And I'm going to write as my answer 4.5 times 10 to the third. That's showing the correct significant figures, because with multiplication and division, the least number of significant figures that goes into the calculation, that's all you can trust when it comes out the other side. Okay, that's the easy one. The hard one is addition and subtraction. That's the one that's going to mess you up. You will make mistakes with addition and subtraction. Try to minimize it. I make mistakes with addition and subtraction. It happens all the time. If I look at a series of numbers, like maybe I want to add those numbers, the best way to do this is literally write it out on your paper. Draw them longhand, and then draw a red line or draw a line after the least precise number. Not the number with the least significant digits, but the least precise one, the one that gets into the smallest minutia. In this case, the 7 and the 2 for the 17 and the 42, that's really where it runs out. I don't know what digit is after the 7 or what digit is after the 2 and 42. It's a measurement. There's some uncertainty there, but I don't know what it is. And if I can't trust what comes after the 7 or what comes after the 2, I don't know what I'm adding to the 3. So when you punch this in your calculator is going to say 65.3, but that 3, you can't trust it because you added two completely unknowns to it. You have no idea what they are, so you can't know what comes from them. So just draw a line down there, and everything that is on the left, you can keep rounding it. So in this case, 65.3, 3 is less than halfway up. So just throw away the 3. If it was an 8, I would round it up to 66. But I'm going to write 65 centimeters or milliliters or whatever my measurement is. Okay, you good with this? So addition and subtraction, least that goes in is all you can take coming out. Addition and subtraction, go slow on this one. Write it out longhand. You can punch it into your calculator, but then round off your calculator based on where the precision runs out. Okay. And when we do more complex operations, like when we're talking about doing first addition and subtraction, and then a multiplication and addition and subtraction, you have to pay attention to order of operations, so you know which one to use at different points. The order of operations is you always do the calculations. You do anything that is in parentheses first. That's kind of your way of saying make this a priority. Anything that's in parentheses, do that first. Then do multiplication and division. Then do addition and subtraction. Now, for example, in that first one, well, before I tell you that, there are some parentheses in the numbers that are invisible, that are hidden. So, for example, when you have a horizontal line for division, when I say A plus B over C, the stuff above and below the line has parentheses, even though you haven't written them in. So be aware some of the parentheses are invisible, and you still have to do them first. And if you take a look at the other one where I have powers like a to the third, okay, exponentials are also invisible parentheses. A to the third, I have to process that third power before I do the subtraction or multiplication and so forth. All right, so here's a couple examples. 53.6 plus 79.4 times 1.503. What is my answer paying attention to significant figures? Do you got to guess? And if I ask people to guess, they'd probably say, maybe 3 significant figures. Least in is all I can trust coming out. Okay, but be careful. There's an addition and subtraction in there. And like I said, that's the one you got to be careful about. So if you do this, what's the first thing you do? Well, anything in parentheses is first. There's explicit parentheses there, so I do those first. I add those two. And if I'm going to add something, I'm going to do it longhand. When I add it longhand, if I take 53.6 and I add 79.14, I get, looks like 133.0. Okay, do you see how the addition and subtraction, the significant figures went up? I added something with 3 to something with 3, and I got something with 4. That's because addition and subtraction, sometimes the significant figures can go up, sometimes they can go down. It's more tricky than multiplication. So I do that calculation first, replace that in my equation, and now I have 133.0 times 1.503. Now I can do the multiplication. Multiplication is easy. Punch this into my calculator. I've got 4 sig figs times 4 sig figs. Whatever my calculator tells me. In this case, my calculator tells me 199.899. Okay, I can work with that. But my calculator doesn't know significant figures. I do. I am responsible for putting only what is true on my my paper, plus an estimate, and nothing that is calculator noise. So you cut that off after the 8, because 4 sig figs times 4 sig figs, you can only keep 4 sig figs coming out. So after the 8, I round off. That's more than 100%. So I'm going to end up writing, what did you write? You wrote 199.9. Put a box around it, you're done. Okay? Like I said, be careful with addition and subtraction. Look at the second one. See the second one over there? 4 sig figs divided by 17.9 minus 15.7. Any bets on that? You think I'm going to get 3 sig figs? Maybe 4 like the first one? Let the numbers talk to you. Okay? Go through, do it slowly, step by step. What do we do first? Anything in parentheses? There's no, oh, there is parentheses. Those vertical division marks, anything above the line and below the line is in parentheses, has to happen first. So the first thing I got to do is 17.9 minus 15.7. Do it longhand. If you do it longhand, you're going to see that I've got 17.9 minus 15.7. If I subtract those, draw a line after them, you're going to see the tens disappear, and I end up with something like 2.2. So my significant figures went down. In the first one, I added 2 numbers that each have 3 sig figs. I got 1 to 4. This time as I subtract 2, I got something with 2 significant figures. Pay attention. Addition and subtraction is the one that will mess you up. Anyway, 2 sig figs. Stick that back into my original equation. Now I got a number of 4 significant figures divided by a number of 2. Plug that into my calculator. And my calculator tells me 2010.9. Okay, but my calculator doesn't know significant figures. I'm responsible for the significant figures. So I draw a line after the 0, the first 0 in 2010.9. Round it off. Okay, now I got a dilemma here, right? When I round that off, I've got 2000. And I know my answer has 2 significant figures in it, because I just went through the work to figure that out. So how do I represent 2000 to 2 significant figures? Do I write 2000 with a decimal point? Because I can't just write 2000. No, 2000 with a decimal point would be 4 significant figures. There is no way to write this answer correctly with standard notation. You have to use the other tool in your toolbox, scientific notation. So how do I write 2000 with 2 significant figures in scientific notation? I write 2.0 times 10 times 10 to the third. Put a box around it. I'm done. All right. Okay. So managing measurements, taking measurements, interpreting measurements, and representing measurements, this can get a little bit tricky. All right. Here's some additional practice. The following numbers are measured. What is the product of 190.6 and 2.3? What do you think? I'm talking about 190.6 times 2.3. My calculator tells me 438.38. Do you buy that? Okay. The some of that is calculator noise. Where do I cut it off? Well, it's multiplication division. 4 significant figures times 2 significant figures. I can only keep 2. I cut it off after the 3. After the 3, well, what's after that is more than 50% to the next digit. So I write 440. Or what I could do is 4.4 times 10 to the second. Either one of those two is valid. All right, here's another one. Let's say I've got 3 numbers I need to add them. 125.17, 129, and 52.5. Any bets on what how many sig figs come out? Don't take bets on addition and subtraction, okay? It's a bad bet. Write it out longhand. 125.17, 129, 52.5.2, and I add it. Now, I got 5 sig figs, 3 sig figs, 3 sig figs. So what? I keep 3 sig figs? Oh, maybe. I'm going to look for where these things run out, where the precision runs out. Which one of those 3 is the least precise number? It's the 129, right? That cuts out after the singles. Doesn't even get into the tenths. I don't know what the tenths value is for that middle measurement. It's 1 for the first one, it's 2 for the second, but it's unknown to me for the third. So when I add these things, and my calculator tells me 306.37, well, I can't trust that 3 because I don't know what came after the 9. So I have to round it off after the 6. Well, what's after the 6 is less than 50% of the way there, so I'm just going to call it 306. You good on this? All right. Now let's say I've got a more complex number. This is actually not a number. This is an expression. 15.035 minus 14.966 divided by 3.825. Okay, that's a ton. But like most complicated problems, just break it into a bunch of simpler ones. Remember order of operations. What always comes first? Parentheses. Anything in parentheses comes first. Okay, so do you see any parentheses in there? Kind of. If it's a division written in that vertical format, anything above the line or below the line is in parentheses. So there is parentheses. So if I want to go through and crunch this, I should pay attention to how many sig figs in that top piece. If I go through and subtract 15.035, or from 15.035, 14.966, I end up with 0.069. See how I only end up with 2 sig figs. 5 and 5 gives me 2. Addition and subtraction will surprise you. So that number is really 2 significant figs. 2 significant figs divided by 4 significant figs. Plug that into my calculator, I get all that noise. But I have to round it off after the 8 because that first operation reduced me to 2 significant figures. So this number is going to be 0.018, whatever the units are, or 1.8 times 10 to the minus 2, and whatever units are on there. Okay. Handling these processes are going to be important. All right, that's where we're going to end it for today. The next thing up is working with measurements and doing conversion between, doing scaling within the unit system, doing bridging between 2 different unit systems, and even figuring out the extent of a sample in an entirely different dimension from the extent of that sample, say in mass or moles or grams. And we will talk about that with context, with the context of significant figures next time. I'll let you go. I hope you have a great night. Bye-bye.